illustration number 12, in which we have to prove that the binding energy of a satellite revolving around the Earth and remaining close to the surface of the Earth is 1 by 2 mg Re. Now here first of all, it is necessary that we should define that this satellite is of which kind. And here the satellite is remaining close to the surface. So basically it is a polar satellite. Now here the necessary centripetal force which is required for the circular motion of the satellite will be equal to the Earth's gravitational force, that is Fg. Now here I am considered that the mass of the satellite is small m, and by writing some mathematical steps regarding to this, then mv square over re, because it is very nearly to Earth's surface, so I can put directly the radius of the Earth, is equal to the gravitational force is given by gmem upon re square. So this is equation number 1, and this arrangement or this equation will give us kinetic energy of the satellite. So equation 1 gives the kinetic energy of the satellite. Therefore, half mv square is equal to gme into m divided by twice of re. But what is the value of small g? The value of small g is written in terms of gme over re square, and therefore I can write down kinetic energy K is equal to 1 by 2 m into g into re. So this is your third equation, and this is the second relation. Now here, if you want to simplify it again, then substitute the value of gme over re square is equal to small g, so it is m into g. So it is now gravitational force. Now the total potential energy or simple potential energy, that is Q, is equal to minus g me into small m over re is equal to minus gme over re square into m into re, because we have multiply and divide the equation by re. Now this particular term is the gravitational acceleration small g. So substituting the value, we will get u is equal to minus G into M into Re. So this is the fourth equation. Now, the total energy E is equal to K plus U. Here K is the kinetic energy, that is 1 by 2 mgre minus gmre. And by using or simplifying this equation, we will get minus 1 by 2 mg into Re. So as we know the relation between binding energy and escape energy, so the binding, and so suppose this is escape energy or total energy, then the binding energy is equal and opposite to this. Therefore, the binding energy is equal to 1 by 2 mg Re, because it is equal and opposite to the escape energy. And with this, our illustration number 12 is over. Two objects of masses 1 kg and 2 kg respectively are released from the rest when their separation is 10 meters. Assuming that only mutual gravitational force acts on them, then we have to find out the velocity of each of them when the separation becomes 5 meters. So first of all, the initial velocity of both the particles are 0, and hence their kinetic energies are also 0. So the velocity of first particle is 0, velocity of the second particle is 0. Due to this, the kinetic energy K1 means of first particle is also 0 and the kinetic energy of the second particle is 0. Now I am assuming something, that when the separation becomes 5 meters, then the velocities of particles are v1 dash and v2 dash respectively, and by replacing this v1 by v1 dash, we have the kinetic energies as k1 dash and k2 dash respectively, and for this system of two particles, the potential energy U at initial stage it is given by the equation U is equal to minus G M1 M2 divided by R1. So here the value of G is 6.67 into 10 to power minus 11 into the mass of first particle is 1 kg and mass of the another particle is 2 kg, and the distance between them is 10 meter. And now by simplifying this, we will get the initial potential energy U is equal to minus 13.32 into 10 to power minus 12 joule. So this is the initial potential energy, and final potential energy U is equal to minus G M1 M2 divided by R2 is equal to minus 6.67 into 10 to power minus 11, 1 into 2 divided by 5. So, U is equal to minus 26.64 into 10 to power minus 12 joule. So here the change in the potential energies occurred. Therefore, delta U is equal to minus 26.64 into 10 to power minus 12 minus the first value 13.32 into 10 raised to minus 12 joule. So the change in the potential energy comes out to be minus 13.32 into 10 to power minus 12 joule. Now, according to the law of conservation of mechanical energy, K plus U means the total energy should be constant, and therefore delta K plus delta U means change in the kinetic energy as well as the change in the potential energy should be 0, and from this the value of change in kinetic energy can be also obtained. Therefore delta K is equal to minus delta U, and therefore the change in kinetic energy delta K is, I am writing in this way, K1 dash plus K2 dash minus 0. This is the final kinetic energy. This is initial kinetic energy. It is equal to minus delta U, and the value of delta U is with us. So it is minus 13.32 into 10 to power minus 12, and therefore substituting the values of K1 dash, so it is half m1 v1 dash square plus half m2 v2 dash square is equal to plus 13.32 into 10 to power minus 12. Now, dividing the equation or substituting the values of m1 and m2. So first value will be half v1 dash square plus here m2 is equal to 2. So 2 2 are cancelled. So it is plus v2 dash square is equal to 13.32 into 10 to power minus 12. And therefore we have this equation now, and also according to the law of conservation of momentum, final momentum is equal to initial momentum. Therefore, m1 v1 dash plus m2 v2 dash, and initially the velocities were 0, so obviously their momentum will be also 0. And now I am arranging the terms in this way. Therefore, now I have only the value of v1 dash is equal to minus m2 over m1 v2 dash, that is my equation number 1. In order to find out the magnitude of v1 dash, it can be done by using this equation mod v2 dash. Now what is the value of mod v2 dash over here? Or before substitute the values of m2 and m1. So it is 2 by 1. So v1 is equal to twice v2 dash. And now substitute the result in the equation. v1 dash square by 2 plus v2 dash square is equal to 13.32 into 10 to power minus 12. So it is basically this equation, and I am giving it as a number A. Therefore, from equation A and equation 3, we have, instead of v1 dash square, now I can write down twice v2 dash whole square divided by 2 plus v2 dash square is equal to 13.32 into 10 to power minus 12. Therefore, 4v2 dash square divided by 2 plus v2 dash square is equal to 13.32 into 10 to power minus 12. Now, simplifying this, 2 to the 4. So it is 2 plus 1. So total 3v2 dash square, and right hand side is as it is. And therefore v2 dash square is equal to, dividing this result by 3. So 4.44 into 10 to power minus 12. And now taking square root on both the sides, therefore v2 dash is equal to 21.07 into 10 to power minus 5 meter per second. So this is the velocity of this second particle, and now from equation 3 I can find out the velocity of the first particle, that is v1 dash is equal to twice of v2 dash is equal to 42.14 into 10 to power minus 5 meter per second, and hence illustration number 13 is over. Now let's move on to the last illustration of this chapter. Illustration number 14. Two satellites S1 and S2 revolve around a planet in two different but co-planar circular orbits, and they are in the same direction. If their periods are, so suppose this is the time period of first satellite, 31.4 hours, and the time period for the second satellite is 62.8 hours. And here the radius of the orbit of satellite S1 means R1, or you can say it is small r, 4,000 kilometers, and now we have to find out R2. Now we know one relation for the first, I am writing over here. According to Kepler's third law, the time period or the square of the time period of the orbit of satellite is directly proportional to the cube of the orbital radius of satellite. And similarly, if I am writing this relation for first satellite and for second satellite, and now taking the division of these two time periods means T1 square over T2 square is equal to R1 cube divided by R2 cube, and therefore my target is to find out radius of the second satellite, that means R2, and therefore R2 cube is equal to R1 cube into T2 square divided by T1 square. Now this R1 cube means 4000 cube, and here 62.8 whole square divided by 31.4 whole square. Therefore R2 cube is equal to 4000 cube into 31.4 is divided by 62.8 by remainder 2, and hence it is 2 square, so it is basically 4, and now I can take cube root on both the sides. Therefore R2 is equal to 4000 into 4 raised to 1/3. Now 4 raised to 1/3 is approximately 1.588. So the answer or the radius of the second satellite S2 is given by 6352 kilometer, and from this radius you can say one thing, that this can be our Earth also, because the radius of the Earth is around 6400 kilometer, and this radius is very nearly to our Earth, and so it can be either geostationary satellite also. The other thing which is asked over here is the magnitudes of the velocities of two satellites. We know the velocities is given by circumference divided by time interval. So it is twice pi r1 divided by t1. So substituting all the values, 2 into 3.14 into the radius is 4000, and the time period is given like 31.4. So the answer will be 800 kilometer per hour. So this is the velocity or the magnitude of velocity of the first satellite. Similarly for the second satellite, V2 is equal to twice pi R2 divided by T2 is equal to 2 into 3.14 into 6352 divided by the time period of the second particle or the second satellite is 62.8. After simplifying, we will get 635.2 kilometer per hour. So from here you can say one thing, that whenever the time period is larger or it is higher, then the velocity decreases. And with this, our chapter number 3 of semester 2 is over.